Hello everyone, I am MD Abu Bakr Siddiq, a master's graduate student in manufacturing engineering program at UTAP and master's research assistant under the supervision of Dr. Amit Lopez. Today, among the assigned 5 concepts from chapter 4, um, I will present 2 topics of them relevant to IBB as a team. My other 3 team members will present other 3 concepts. I will present mainly requirements, verification metrics, and hierarchical VBT optimization. First, I will go to RVM. So what is RVM? Here is the template for RVM. Actually, to develop an RVM, first it is required to have some good requirements that need to be fulfilled. The RVM is a document where all the requirements for the systems are listed and giving a traceability ID. In the following slides, I will show you the systems requirements for our project Tron Food Delivery. For each requirement, it is required to determine the type of methods that will be used for verifying the requirements. There are various methods like analysis, inspection, demonstration, test, and certification. The RVM additionally requires the identification of the development stage where this test will take place. And these stages are definition, design, implementation, integration, and qualification. So here is the list of our requirements for our project. Total 23 requirements that we got after instructors review and some peer reviews. Okay, we need to develop an RVM. Here you can see the developed RVM for our drone food delivery project. All requirements have traceability ID based on functionality, communication, and performance. For example, requirement number 17, the system shall have a backup battery ensuring the operational duration of at least 30 minutes to secure return to base. It is a performance level requirement, as this requirement is related to some other factors like activation signal of a sensor for backup battery, critical power levels of main battery, and many other subsystems. So we can verify it in integration phase, because in integration, the combined subsystems are verified. Another important concern is verification methods. For our project, we used some symbols to define verification methods. In this slide, the meaning of the used symbols in RVM is shown. To go back our example for requirement 17, we use this symbol, and that is basically a testing method. More specifically, it is a performance test. Like we will need to test the performance of the backup battery to ensure whether it is working or not when it is required, and the specific duration of time. Now, hierarchical VBT optimization, what is the goal of it? Basically, the goal is to improve the VBT plans, and we can reduce or eliminate redundant or repetitive VBT activities so that cost is minimal. For hierarchical VBT optimization, initial RVMs of the systems, subsystems, and components are a prerequisite. From this diagram, here we can see system level requirements on is allocated to subsystems A, and then allocated to components AA and AB. In RVM, we saw verification methods consist of analysis, inspection, demonstration, testing, and certification. Similarly, the verification steps often followed typical system components sub-components phases. The optimization process requires reviewing each requirements at each hierarchical level and determining in which VBT activities could be eliminated. For example, reviewing the example depicted here in the diagram may suggest that requirement on could be tested at the subsystem level and may not require a proof at a system level, as it must be made in its entirely at the subsystem A level. Now going back to our RVM, uh, the last portion is mainly for VBT optimization. Here you can see which level we verify the requirement is indicated. For example, for requirement number 1, system shall incorporate all business hours to have available drones. It is more about the system's overall functionality that is dependent on many other factors and subsystems. It is possible to check and verify this requirement at each level, like components level, subsystem levels, and systems levels. However, these are redundant and might cost huge. So we may only verify it at the system level to reduce the cost and time required to perform it. In the same way, for every requirement, we set priority when it is a must to perform its verification. Thus, we can reduce the overall cost and time consumption. And this is how hierarchical VBT optimization works. So, hierarchical VBT optimization mainly reduces VBT activities, and we can get a shorter version of RVMs. It is like what is depicted here. In the initial phases, there are lots of activities for the systems, subsystems, and components level. But after conducting the optimization, we can get less activities to be performed like this on.
Since system requirements need to be understood by everyone involved, like users, developers, testers, or stakeholders, they're usually described in natural everyday language. However, describing complex systems with natural language can bring its own problems, like ambiguity, inaccuracy, or inconsistency, leading to different interpretations. That's why it is crucial for the VBT team to carefully validate all system requirements for both testability and quality through methodologies like the following three: evaluating requirements testability, evaluating requirements quality by attributes, and evaluating requirements by syntactic and semantic means. The first method is evaluating requirement testability. Testability can be defined as the degree to which a requirement is set in terms that permit establishment of test criteria and performance of tests to determine whether those criteria have been met. In this sense, requirement testability analysis verifies whether the requirements are indeed testable, so that any requirement can be used to prove or disprove whether the behavior of the system is correct or not. As this evaluation can get tricky, there are certain attributes that are recommended to be met while carrying out this test. For example, operability is the ability to operate satisfactorily under both normal and slightly abnormal conditions, which are different from the design conditions. Controllability is the ability of an external user to affect system elements in its entire configuration space using only external inputs. Observability is a measure of how well the internal states of a system can be inferred by knowledge of its external outputs. Composability relates to the ability to be broken into components or basic elements. Stability is the capability of a system to behave in the same way and produce the same expected sequence of outputs for any given initial state and a specified sequence of inputs. Understandability is the capability to be understood by a person with a reasonable knowledge of the subject matter. And simplicity, which is related to the burden of it puts on someone trying to understand it. Requirement testability may be performed by evaluating each of the requirements individually for testability by means of the attributes defined before, and be designated testable only if the test attributes regarding the requirement can be answered positively, giving form to the requirement testability matrix shown here as an example. The second method is evaluating requirements quality by attributes. It analyzes the quality characteristics of each requirement and helps to understand if the requirements clearly state what actions must be carried out by the system under specific conditions. As in the previous method, a quality requirement must possess some attributes, such as being traceable. That means it must have a unique identifier. It must be understandable, so it's clearly understood by everyone involved. It must be precise, so it's unambiguous about its bounds. It must be succinct. That means it describes only the necessary information and not additional details. It must be clear, so it's described and understood in a simple manner. It must also be uncompounded. That means that it must not have any other requirements or sub-requirements in it. It must be also correct. That means it must reflect the true wishes of the customer. Also, it must be complete. That means that it must give all the relevant information on what is required. It must be consistent with other requirements. That means that it must not enter in conflict with the other requirements. It also must be unambiguous, so it has one and only one interpretation, and also feasible. So that means that there must be a known way to be accomplished. Each system requirement should be analyzed using the characteristics defined before and approved if it meets all the defined qualities attributes, giving form to the requirement quality matrix shown here as an example. The last method evaluates the quality of requirements through their syntactic and semantic attributes. That is, it evaluates the quality of requirements by recognizing certain syntactic or semantic traps used in them, certain words, certain phrases, or grammar. This method can be carried out by software tools and provides a quantitative, corrective, and repeatable evaluation of requirements documents by using certain indicators, such as optionality, when it contains optional parts, words like possibly, eventually, if case, etc. Subjectivity, when it contains feelings or opinions, words like similar, better, worse, similarly, having in mind, etc. Vagueness, when it contains not quantifiable words, clear, easy, difficult, strong, bad, efficient, etc. Weakness, when it contains a weak main verb, like can, could, may, might, should, etc. Implicity contains when it contains a subject that is more generic than specific, like this or previous, next to, next, above, below, etc. Multiplicity when it contains more than one main verb, direct or indirect complement, words like or, etc. And finally, an explanation when it contains an acronym that was not explicitly defined within the requirement document itself.
Section 4.3.5 talks about failure mode effect analysis. The failure mode effect analysis is a procedure for analysis of potential failure modes within a system or a given process. Part of this procedure is determining how to eliminate such problems. To accomplish this, we first have to identify the potential problems that may occur. Then we identify the cause or the causes for those problems. The third step is to determine the frequency with which they may impact the system. We then estimate the effect of these failures, and the last two steps are to determine how to detect and/or how to prevent those failures, and then later on take corrective actions. The diagram to the right shows a typical failure mode effect analysis, displaying a system or a process in place that, after understanding the functions of it, we then ask what can go wrong, what are the causes and effects, how bad and how often does it happen, and how to prevent it to later on modify the system. There are 4 basic types of failure mode effect analysis. First, there's the design failure mode effect analysis. This procedure is performed during the design phase, and this leads to a better understanding of design deficiencies, and it's done in an early stage of the system development, which allows for corrections, and this reduces impact of these failures. Then there's the functional failure mode effect analysis. This one focuses on the intended function or the intended use of a system. It can be approached by analyzing the potential problem or loss from each potential loss of functionality, or we can estimate the statistical probability of the problem. The system failure mode effect analysis is a white box, since it can be used to analyze the system at any level. The process failure mode effect analysis is mostly performed on the manufacturing process, and it identifies the possible failure modes in the manufacturing process, like limitations in resources, equipment, tooling, training, and other potential sources. Then we have the failure mode effect analysis standards, which provide sample inspection forms and instruction documents. These standards also identify criteria for quantification of risk associated with potential failures. Some examples are the ones provided here. The first one describes a method used mostly by government, military, and commercial organizations worldwide. The second one is based on a procedure defined by major international automobile companies, as well as their suppliers. And the third one is recommended for non-automobile applications. The implementation of the failure mode effect analysis can be divided into 4 steps. Step 0, which is preparation, and it consists of having a clear understanding of the process that will undergo the analysis. Step 1 is severity determination, which consists of determining all the potential failure modes based on the functional requirements of a system and their effects. We have severity evaluation criteria to know the ratings of each effect. Step 2 is occurrence determination, which consists on looking at the causes and their frequency. This will rate the failures in a range of 1 to 10. Step 3 is detection determination by design control. A detection rating represents the general ability to detect a system defect or a failure mode by using a planned set of tests and inspections. Basically, the test engineer here looks at the system mechanisms that are responsible for detecting potential failures. Step 4 is computing risk priority numbers, or RPNs, which are quantitative determination of risk based on multiple factors. And it is defined as the product of S, which is severity rating, O, occurrence rating, and D, detection rating. This values for each failure mode. The failure modes that have the highest RPN, or risk priority number, should be given the highest priority for taking corrective actions. So they should be the first ones on the list when modifying the system. The applicability of this section to our projects, it's with the cost-benefit analysis that each team was requested to submit this last week. In this cost-benefit analysis, each team determined what were the potential failures that our systems could face, as well as their severity levels, the risks as well of not meeting the requirements. And this is an example of what Group 1 did with the drone food delivery cost-benefit analysis. And this only shows the first 3 requirements. The first column that we saw after the requirement was the probability of the failure. Each team rated each of our risks from 1 to 10, 1 being the lowest, 10 being the highest. Then we rated the severity to get the total, the probability of the severity. We then got the cost, the appraisal cost and the impact cost. And the next actions that our teams will have to take is to see the more severe risks or potential failures so we can take corrective actions on them.
Here are the different review methodologies listed in this chapter. 1 is expert team reviews. These are inspections, walkthroughs, audits, and peer reviews. Another approach is formal technical reviews. These are detailed out in Table 4.13. A few of these are PDRs, CDRs, and PRRs. The last methodology mentioned in this chapter is a group evaluation and decision, which consists of brainstorming, consensus agreement, parliamentary procedure, and modeling group decision making. Below is listed the process of document inspections. Document inspections are disciplined engineering practice for detecting defects in technical documentation. Step 1 is inspection planning. The inspection leader plans the inspection and selects the inspection team. Step 2 is the initial meeting. During an initial meeting, the author of the work product explains the document or software code to the inspection team. Step 3 is the inspection preparation. Each inspector on the team examines the document or software listing to identify possible defects. Step 4 is the inspection meeting. During the inspection meeting, the document or software listing is discussed section by section, and the inspectors point out defects for every section. The meeting ends with the writing of an action plan. Step 5, product correction. The author makes changes to the work product in accordance with the action plan from the inspection meeting. Step 6 is inspection follow-up. The inspectors make sure that all problems have been eliminated by checking the changes made by the author. On this slide, I will be going over the general process of formal technical reviews. Step 0. The review leader is expected to use a standard checklist of entry criteria to ensure that optimal conditions shall exist for a successful review. Step 1. Responsible management ensures that the review will be appropriately resourced with staff, time, materials, and tools, and will be conducting according to policies, standards, or other relevant criteria. Step 2. The review leader identifies or confirms the objectives of the review, organizes a team of reviewers, and ensures that the team is equipped with all necessary resources for conducting the review. Step 3. The reviewer leader ensures that all reviewers understand the review of goals and the review procedures. In addition, he or she is responsible for making all necessary material available to the participants, and all relevant procedures for conducting the review are well known. Step 4. Reviewers individually prepare for group examination of work under review by examining it carefully for anomalies, the nature of which will vary with the type of review and its goals. Step 5. Reviewers meet at a planned time to pool the result of the preparation activity and arrive at consensus regarding the status of the system and activities or documents to be reviewed. Step 6. The persons responsible for the reviewed objectives undertake whatever actions are necessary to satisfy the requirements agreed at the review meeting. The review leader verifies that all action items are closed. Step 7. The review leader verifies that all activities necessary for successful review have been accomplished and that all outputs appropriate to the type of review have been finalized. On this slide, I'll be going over the guidance for technical reviews. Each formal technical system should have a clear and predefined set of objectives and clear statement of purpose. It is also always advisable to conduct a meaningful set of internal reviews first, and they must produce honest criticism. Furthermore, training reviewers in formal technical system review procedures and techniques prior to assigning them to a project is most advisable. Scheduling technical reviews too early, before relevant system documentation and work procedures products are available, may lead to decisions based on insufficient information. Conversely, scheduling technical reviews too late can mean the project commitments have already been made, which cannot be changed without incurring heavy financial or time losses. Within technical reviews, careful attention should be paid to areas that contain new or unfamiliar problems. It is good practice to call in outside experts to provide such advice. It is also recommended that the review team be comprised of representatives of customer and relevant stakeholders, the program manager, the chief system engineer, one or more quality assurance configuration control and process improvement representatives, and one or more system developers, maintainers, and user domain experts. Keep in mind that too many reviewers may create havoc in the reviewing process. On this slide, I'll be going over the group evaluation and decision process. The first phase of the group evaluation and decision process starts with the group orientation and development of shared mental model of the issue. More specifically, the group tries to arrive at an accurate understanding of the system to be evaluated by means of discussion, as well as exchanging and sharing information. If initial evaluation of the data available to the group identifies a problem, then the nature of the problem, the extent and the seriousness of a problem, as well as likely cause of the problem, and the possible consequences of not dealing effectively with it, are analyzed. Based on this analysis, the group generates a number of appropriate and feasible alternative lines of action, among which an acceptable choice of one or more actions should exist. During the next phase, the group uses one of the several decision schemes to select a single alternative line of action from the various alternatives originally proposed by the group. Typical decision schemes are an individual, usually the managers, who make the decision for the group, voting using a majority rule, consensus rule, and so on. During the last phase, the group reviews the implementation of the selected solution and evaluates the consequences of this process. In particular, the group needs to be fully cognizant of relative merits and disadvantages of all available alternatives in order to learn how the group can be more effective in the future. More specifically, post-mortem discussions provide valuable learning lessons to the group, facilitating a retrospective look at past decisions and the decision-making process itself. On this slide, we'll be going over the risks for group process. Shared information bias is a tendency for groups to discuss issues familiar to all members and avoid examining information that only a few members know. This leads to a poor decision-making due to ignorance of important facts by the group. Poor communication skills, as well as biases in individuals' cognition and motivation, can often lead to judgment errors on part of the individuals in the group. Research in social comparison theory identifies that phenomenon of a group polarization, the tendency to respond in a more extreme way when making a choice as part of a group. Under this condition, a group has difficulty assessing the facts rationally and often fails to reach a decision acceptable to all. Groupthink is a psychological phenomenon that occurs within a group of people when desire for harmony or conformity in the group results in irrational or dysfunctional decision-making outcome.